In this slideshow, I'm going to go over some basics of the identification of an unknown metal lab and give you some direction for how to approach the calculations in this lab. It's a very calculation-heavy lab. It utilizes some concepts that we will not possibly have gone over in class yet. So the purpose of this video is to summarize some of those concepts. We'll develop them more fully in class, and then to give you some guidance on how to use those concepts to do the calculations. I'm not going to do actual sample calculations in this video. Setting up and working the calculations is up to you, so you need to figure out how to use how to set up these equations from the information that I've shown in this video, but this should help out a lot. So basically what you're doing in lab is you are taking a metal and you're putting it in hydrochloric acid. So sometimes when we want to talk about metals generally, we use a capital M. So don't confuse that capital M with something like molarity or molar mass. In this occasion, it just stands for a metal. So we're trying to identify this metal, and we're going to take some amount of it, and we're going to combine it with an aqueous solution of hydrochloric acid in a flask. Okay, and this is what the reaction will end up looking like. The reaction should go to completion, and each metal will have combined with chloride ions in the stoichiometry that's shown in this equation, and then give off an H2 H2 gas molecules. So how this works is the reaction happens over in this flask here, and then the hydrogen gas that is produced is going to travel through the apparatus down to this tube, which is filled with water. And what's going to happen is that these bubbles of hydrogen gas are going to displace the water. Okay, so that eventually you'll get a gas up to some level in this graduated test tube here. Okay, so that's the basics of the setup. The goal is to determine the identity of the metal through its molar mass. And we abbreviate molar mass with big M subscript little m. So one of the M's stands for mass and one of them stands for molar. Okay? So before I go on, I want to think to yourself, if we weigh our sample of the metal that we use in the beginning here, what other piece of information do we need to know to determine the molar mass of that metal? Okay, so think to yourself of that, and then maybe if you have time, think about how might we determine this. I'll give you a few seconds to think about that before moving on. And note the units for molar mass is grams per mole, so take that as a clue. Okay, so hopefully what you've done was think to yourself, okay, molar mass is grams per mole. I already know grams because I have weighed my sample at the beginning, so I'm going to know how many grams of metal I'm putting in here. The other piece of information that I then need to know in order to calculate the molar mass is how many moles of metal are in that sample. If I know that, then I can divide the mass, grams, by the moles and get grams per mole, or the molar mass. So our whole goal is actually to figure out how many moles of metal are in that sample. And we're going to use some roundabout logic and calculations that are actually pretty elegant in order to get to that. We're going to use this reaction to answer that question. Okay, so here's an overview really of what you're going to be doing calculation-wise in the lab. So you are going to read, you're going to do this reaction, and eventually you'll get a gas bubble that goes to some level in this test tube. You're going to record the amount of volume of gas. From that volume of gas, we're going to use some things that we know about gas properties to calculate the pressure of that gas. And the gas in this case that we're interested in is H2. Okay, why H2? Because it is related through stoichiometry to the number of moles of that metal. So if we know this, if we know how many moles of H2 we're generating, we should be able to figure out how many moles of metal we're generating. So that's kind of what the logic is here. If we know the volume of the gas produced, we will be able to find out the pressure of the gas produced, which is hydrogen. Okay. If we know that, then we should be able to calculate the moles of the hydrogen gas that are in this test tube at the end of the reaction. And through stoichiometry, then figure out how many moles of metal there are. And I did use sort of a non-conventional abbreviation for metal here, just because there's a lot of M's, and I want you to know what I'm talking about here. Moles of metal that we're interested in. Okay, if we know the moles of metal, then we can figure out the molar mass, because again, we have weighed our sample of metal. So that's the overall logic. We'll go through some of the details of how to do some of these conversions. Some are more intuitive than others. So we'll talk about how to do these calculations. All right. So this is what you're going to see eventually. You're going to see a volume of gas in your test tube. You're going to want to measure that to the nearest 0.1 milliliter, and the apparatus that you use should allow you to do that. And then there's going to be some water left over in your tube, because our bubbles of hydrogen have displaced some of the water, but not all of the water. And so it's going to be important to measure the height of the water head. This is what this is called, the water head in this test tube. Okay, so remember that our overall strategy is to somehow, from this information that you're going to collect, this really is your only data from this experiment, is volume and height of the water head. But somehow you're going to figure out what the pressure of H2 is, and then from that figure out the moles of H2, and then the moles of your metal, and then the molar mass of your metal. So how do you do that first step of going from those two measurements that you make in the apparatus, the volume of the gas and the height of the water head, to figuring out how much hydrogen gas, how much pressure of hydrogen gas there is? And in class, we will have started talking a little bit about what pressure is. Okay, so here's an equation. So it turns out that you have the pressure of the atmosphere all around you. So there's atoms and molecules of air that are constantly creating pressure around us. That's atmospheric pressure, and that's this term here, PATM. The atmospheric pressure is pushing down on this water, okay? Everything else in this tube here is pushing back. So the pressure that's created in this tube is equal to the atmospheric pressure, because this volume is not changing. So that's what this equation is saying. So the pressure outside of the tube is equal to the pressure inside of the tube, and there's three components to that pressure inside the tube. As I go through them, remember our goal is to figure out the pressure of just the hydrogen gas. So first of all, there's pressure that is related to the water in the liquid state of that test tube. If we go back to our picture, right, there's still liquid in our tube, and that's pushing down, and that creates some pressure. That is some component of the pressure that's equal to this atmospheric pressure from the outside. Okay? Another component of that pressure is water. And the reason why is because we are bubbling hydrogen gas through water. So as the hydrogen gas bubbles up through the water in this test tube, some of the water too is going to vaporize and turn into water vapor. And so what you actually get in this bubble is not pure hydrogen gas. It is hydrogen gas mixed with water in its vapor state. So if we can find out how much water there is in that tube, how much pressure there is in that tube that is due to the water in the gas state that occupies that volume, then, and if we know these other values, then we should be able to figure out the pressure of just the hydrogen gas that's also in that bubble. So all of these three pressures here add up to equal the atmospheric pressure. Okay, our unknown is the pressure of hydrogen gas. That's what we're interested in. So how do we do this? First of all, atmospheric pressure is something that you can measure. There will be a barometer in the lab, and you can just take the measurement off of that barometer. That's easy. You may have to convert that into another unit, type of unit, for the purposes of these calculations. So just a word of caution for you, there is a lot of dimensional analysis in these calculations, and you need to really pay attention to your units. Okay, so that's easy. You measure it and maybe convert it into another unit. How do we figure out the pressure of water in its gas state? Well, that's a property that is called vapor pressure. And that's something that we will talk about later in class. It's basically the pressure of a gas above a liquid. So there's always some pressure of a gas above a liquid due to a fraction of the molecules escaping into the vapor state, and that's dependent on temperature. So you will get a table of vapor pressures so vapor pressure is dependent on temperature. So you'll get a table in lab or in your lab manual that tells you at certain temperatures, and you'll want to measure the temperature of the room, what the vapor pressure is of water, and that's going to be the term there. Finally, how do we figure out the pressure of our liquid water head, the thing that's called the water head? So this is a rather unconventional calculation for a chemist. We don't usually use this equation, but it's useful in this case because we're dealing with liquid water that's pushing down. We can use three properties here to figure out the pressure of that liquid water. One is the density of water, okay? One is the constant that reflects the acceleration due to gravity, because gravity is what's pulling that water down, and how much it's pulling that water down is dependent on how dense the stuff is that it's pulling down. And then the height of that water head, so how much water actually is there, okay? This looks like an innocent enough equation, but there is going to be a lot of dimensional analysis involved in this calculation. So your lab manual tells you about the density of water. It gives you that density in terms of grams per centimeters cubed. You will actually need to convert that into, I believe, into kilograms per meters cubed. I double check the manual to make sure that that's correct. And so in order to do that, you're going to need to know how to treat cubed units in dimensional analysis. So for that, you're going to want to look at section 1.8 in your book. Okay? The acceleration due to gravity is listed in your lab manual, and the height, of course, is something that you'll measure, and you'll have to convert that to meters too. So in order for this calculation to work, all of these things have to use the same types of units. For example, there's kilograms in this acceleration due to gravity constant, and so there has to be kilograms in your density too for them to cancel out. So that's the challenge of that calculation, is making sure that you have all of the right units so that they'll cancel out to give you the pressure units that you want. Similarly, when you go ahead and have values, once you have values for all of these three pressures, you're going to have to rearrange this equation to solve for this pressure of hydrogen gas. And so in order to do that, all of these three pressures have to be in the same units. So again, you might have to do some dimensional analysis and look up some different equivalencies for different pressure units in order to do that. So just be mindful of the units and of the need to do dimensional analysis. Okay? So that's how you get the pressure of hydrogen gas. But remember, that's only really the first step. That's not our goal. Our goal is to figure out the molar mass. And so the reason we wanted to know the pressure of the hydrogen gas is because that's going to tell us about the moles of hydrogen that we collected, which is going to be useful in this logic. So the question is, what do we do with this information to tell us how many moles of hydrogen gas we have? And the answer to that question is, so we're looking at this blue arrow here, trying to take the pressure of hydrogen gas and convert it into the moles of hydrogen gas. The answer to that question is to use an equation called the ideal gas law. And what the ideal gas law is it is an expression of how the pressure of a gas is related to its volume, the number of moles of atoms or molecules of that gas, and the temperature of that gas. R is a constant, and it has several different values with different units attached to it. You can look at table 10.3 in your book to find different values of R. Again, you're going to need to use the one that has the correct units to cancel for all of these measurements that you've taken. Okay, so you will have now calculated the pressure, so that would go here in whatever units you need them to be. You will have measured the volume of that gas in your tube. Okay, you will have measured the temperature of the room. You will know R, again, from table 10.3. And so really what you're after is this N. You want to know how many moles of hydrogen gas are represented. So you're going to use your algebra to rearrange this equation to find N. You're going to make sure that the pressure, the volume, the temperature, and R are all in units that will cancel out with each other to give you moles as your final unit in this calculation. And then you will know the moles of hydrogen gas. So this step of calculating the pressure of hydrogen, and then this step of using the ideal gas law with the correct units to find the moles, those are probably the two most challenging steps. If you pay attention to your units, and if you pay attention to your algebra here, you should be good to go on that. So now the question is, okay, I know my moles of hydrogen gas. How do I figure out my moles of metal? Take a second or two to think about that. Okay, anytime we go from moles of one thing to the moles of another thing that is related to that first thing by a chemical equation, we use stoichiometry. Okay, so that means that we use the mole ratio in that equation. So you have to look back at your equation for that reaction. You need to ask yourself, okay, so for every mole of H2 that's produced, how many moles of metal were used up? And you need to use that stoichiometric ratio to figure out how many moles of metal you have given the number of moles of hydrogen that you have calculated from that equation. We're almost done. So if you know the number of moles of the metal, then how do you figure out the molar mass of your metal? That's the ultimate value that is going to enable you to calculate or to identify the metal that you have. And when you think about this again, think of units. You're going from moles to grams per mole. And remember, you weighed your metal at the very beginning. You know how much metal in grams was in your sample. You now know how many moles of metal were in your sample because you've done these calculations. Now all you have to do is divide the two. Grams per mole is the unit that we want, and so you divide your mass in grams by moles in moles, and you'll get grams per mole. Okay, so that is it for how to set up your calculations. Again, we'll talk more about the basis of the ideal gas law in class. Everything else is dimensional analysis. Be sure to pay attention to units. And good luck and have fun.